ears, right? Peripheral organs. And if you see the anatomy of an ear, it has how many parts? How many parts? 3. External or outer, then what? Middle and internal or inner, right? Outer ear consists of pinna, lobule, helix, and external acoustic meatus. That cannot make sense. Then middle ear is located in which bone? Temporal bone, right? A cavity inside the temporal bone. And inside the middle ear, you have how many tiny bones? 3. Those are called ossicles. Is it clear? And how many tiny muscles? 2. Then in the inner ear, you have a snail-like hard, coiled, bony structure filled with fluid. That is called what? Cochlea, which is the most important part of the ear. Why? Sound receptor cells are located inside the cochlea. Is it clear? And sound receptor cells are called what? Hair cells. Okay. You have other structures in the inner ear, vestibule and semicircular canals. Make sense? Are they related to sound or not? No. They are related to what? Balance. Head position, right? They can detect the movement of the head. You know, they are partially filled with fluid. Now see, if this is a tube, okay, partially filled with fluid, not full. Now if I tilt the tube, fluid will move, right? If I tilt this way, fluid will move this way, right? If I tilt this way, fluid will move that way, right? Make sense? So if I move this tube, the fluid will move too. And inside the tube, you have the sensors. They can detect which way the fluid is moving. Make sense? So now look at my head. If I move my head, the semicircular canals are moving too, right? So fluid is moving inside it. So they can detect which way your head is moving. Make sense? Sending signal to the brain will process that. Okay? So that's how they work. These are partially filled with fluid. So when you move your head, fluid moves inside it. Okay. So let's see those 3 ossicles. 3 ossicles are malleus, incus, and steps. 3 ossicles. First one is the malleus, middle one is the incus, and innermost one is the steps. So those are 3 ossicles. And 2 small muscles, let me write it down. Tensor tympani and stapedius. These are 2 muscles, tiny muscles. And 3 ossicles are malleus, incus, and steps in the middle ear. Now let me draw here. This is the ear, external acoustic meatus. Then this is the middle ear. You have the tympanic membrane or eardrum. This is the eardrum, called tympanic membrane. Tympanic membrane or eardrum. Okay. Now you see 3 ossicles. First one is the malleus. This is the malleus attached to the tympanic membrane. Okay. Then the middle one is the incus, and innermost one is the steps. Okay. So malleus, incus, steps. First one is attached to the tympanic membrane or eardrum, and the other end is attached to the incus, and incus other end is attached to the steps. So you see they are attached to each other like this. And this is important. the other end of steps is attached to the cochlea. This is the cochlea in the inner ear. So this is inner ear and this is the cochlea. So you see here, this steps is attached to the cochlea, beginning of the cochlea, and this is called oval window, where the steps is attached to the cochlea. That is called what? Oval window. Make sense? Okay. So three ossicles are like this. You see, they are attached to each other like this. They are attached to, and malleus is attached to the tympanic membrane, right? So when sound waves enter into the ear, sound waves enter into the ear, they hit the tympanic membrane. From this side, they hit the tympanic membrane or eardrum. So tympanic membrane shakes like this, right? And that moves the ossicles, because ossicles are in the other side of the tympanic membrane, right? So that will move the ossicles like this. Is it clear? Now, why you have three ossicles in the middle ear? Why not one? Because three ossicles are attached to each other and they can move like this at the joints, okay? Move like this at the joints, and that amplifies the sound pressure many folds, many times. So it works like a lever, amplifies the sound pressure many times. These ossicles. Act as lever. So when the sound, see now, goes from here, from the eardrum to the oval window, because of these three ossicles, the pressure increases here many times more than here. Make sense? Many times more because of the ossicles. Number one. Number two is, see, this is another physics. Tympanic membrane is, you see here, bigger than the oval window, right? So if I put pressure on something very big and then connect this one to a small and put pressure here, when the pressure from the big one will go to the small one, what will happen? The pressure will increase or decrease here? Increase many times. Make sense? So same thing happens here. From big membrane, pressure is going to the small membrane, right? So that is another thing that will amplify the pressure. Make sense? The two things are increasing the pressure from the tympanic membrane to oval window. One is the ossicles acting as lever, and another is from big to small, right? The pressure is going from big one to small one. So many times the sound pressure increases. So the pressure is pretty high here. And sound waves are going one after another. You know that. Now you tell me, this is the cochlea. Cochlea is filled with what? Fluid. I mentioned it, right? Fluid filled. Filled with fluid. Okay? Why the pressure should be amplified from here to here? Because when the sound waves enter into the air, the sound waves travel through the air, right? Air. But in this side, sound waves will travel in the water or fluid. So you need more pressure to move the fluid. That's why it should be amplified here. Anyway, so we won't go detail. Just know that when the oval window will shake like this, waves will be created or transmitted to the fluid, from the air to the fluid. And that's why you need to amplify the pressure here to move the fluid. Okay? So now let's go this part. Since it is a coiled structure, I can just hold it and pull, like make it straight, right? If something coiled, I can make it straight, right? So let's make the cochlea straight. So if I make it straight, it's like a long tongue, okay? Make this straight. And see inside. Inside the cochlea, there are two membranes. Vestibular membrane and basilar membrane. So inside the cochlea, there are two membranes. Upper one is called what? Vestibular membrane. Make sense? And the lower one is called what? Basilar membrane. Make sense? Now you tell me, if this is the cochlea and I put two membranes inside it like this, how many partitions I will get? How many? Two partitions, right? So how many chambers I will get? 3. Make sense? If I put two big screens right inside, I will get 3 chambers, right? So now inside the cochlea you have 3 cavities or chambers. Now let's make a slice here. I cut this part and see under the microscope, okay? This is the slice I took from here, and this is the vestibular membrane, this is the basilar membrane. Okay, so vestibular membrane, and this one is what? Basilar membrane. Inside the cochlea, right? And inside the cochlea you have what? Fluid, right? Fluid. So all these 3 chambers are filled with what? Fluid. Make sense? Fluid. And this upper chamber is called scala vestibule. Middle chamber is called scala media, and lower chamber is called scala tympani. So 3 chambers have 3 names: scala vestibule, scala media. Media is the middle one, this one, and scala tympani. Scala vestibule, scala media, scala tympani. So separated by 2 membranes. Is it clear? Okay. So now you tell me, if I see inside the cochlea, how many membranes are there? 2. Upper one is called the vestibular membrane, lower one is called the what? Basilar membrane, right? And how many chambers you got? 3. Scala vestibuli, above the vestibular membrane. Scala media is the middle one, and scala tympani is the lower one. Now, middle cavity is important. Why? On the basilar membrane, see here, this is very important. On the basilar membrane, you have a structure that is called the organ of Corti, also called spiral organ, same thing. Spiral organ rests on the basilar membrane. So this structure on the basilar membrane is called the organ of Corti. Why this structure is very important? Because you know, inside the cochlea you have the receptors. Remember that? I said that that's why cochlea is very important, right? So we need to know inside the cochlea where the receptors are located. Receptor cells are located inside the organ of Corti. So these are the hair cells you see here. and on the hair cells you have hair. So these are the sound receptor cells. Okay, nucleus. So these are the hair cells or sound receptor cells. Sound receptor cells. Now we got it, right? We got the treasure where the most important structures are located. Is it clear? The hair cells are located inside the spiral organ or organ of Corti, which rests on the basilar membrane inside the cochlea. Very good. And here are like this. On the organ of Corti, another organ is here. That is called the tectorial membrane. Tectorial membrane. This tectorial membrane is like a soft jelly-like structure. Soft jelly-like membrane. It's very soft. And since it is soft, the hair, these hair are kind of hard. They get inserted into the tectorial membrane like this. So this is the tectorial membrane, soft jelly, and the hair of hair cells are inserted into it like this. Okay. Make sense? Going inside like this. Oh yeah, the last thing. You see, we are pretty close to finish. Let's go back here. So the sound waves enter into the ear, hit the tympanic membrane. Tympanic membrane shakes. Look at me. Tympanic membrane shakes like this, right? Eardrum shakes. So that also shakes these three ossicles, right? And that amplifies the sound pressure, right? And also from Lord's eardrum, signal pressure is going to the small, so the pressure is amplified. And that causes the movement of fluid here inside the cochlea. Waves are created inside the cochlea, we know that. So what happens here, look at this. When waves are created in the fluid here, that will move the basilar membrane up and down like this. Because basilar membrane is here and fluid is here, right? So waves are created in the fluid, so that will push the basilar membrane up and down. Okay? Like if you put something on water that is floating, right? A piece of board or something floating on the water, when waves are created, that also moves up and down, right? So the basilar membrane will move up and down. Now look at me. This is the soft gel-like tectorial membrane here, and here are inserted into it, right? And basilar membrane is moving up and down like this, so that will do like this. Push the hair cells up and down, make sense? When the basilar membrane moves up, hair will bend. Make sense? Down, straight. Bend, straighten. So every time the hair bends, receptor cells send signal to the brain. Straight, no signal. Bend, signal goes to the brain. Make sense? So if the sound wave is 5,000 times per second, 5 kilohertz sound, the basilar membrane will move 5,000 times in 1 second. Just think that how fast, right? 5,000 times in 1 second. 5 kilohertz sound we can hear. Okay? So 5,000 signals in 1 second will go to the brain. Make sense? And you will listen 5 kilohertz sound. If 10,000 times, you will listen 10 kilohertz sound. Okay? So how many times the hair are bending, that many times the signal is going to the brain. And brain is counting that and processing that. Is it clear? So, now from the hair cells, how the signal will go to the sent to the brain? By these axons. And these axons together form the auditory nerve. So auditory nerve takes the signal out from the cochlea. So this is the auditory nerve. Cranial nerve number 8. Nerve number 8. That takes the signal to the thalamus, and from there to the primary auditory cortex. All of you know that in the temporal lobe here, primary auditory cortex is here located. You studied the brain, right? You did? Brain? Yes. Remember the auditory cortex here? So from the ear, the signal will go to the thalamus, because it is the major sensory relay station. From here, it will go to the primary auditory cortex. Primary auditory cortex in the temporal lobe, upper part of the temporal lobe of the brain, and that will count how many times the signal arrives. Okay, so that's the idea, okay, about the auditory system. Let me quickly go over so you will remember better. So, again, quickly, ear has how many parts? 3. Outer ear, middle ear, and inner ear or internal ear. Okay. Outer ear consists of the pinna and the fold helix, right? And the canal is called what? External acoustic meatus. Is it clear? And middle ear is located inside the which bone? Temporal bone. It is a cavity inside the temporal bone, right? And it has how many ossicles? 3. Malleus, incus, and steps. Make sense? And how many muscles? Tiny muscles? 2. Stapedius and tensor tympani. Okay? Ossicles do what? Increases the sound pressure, amplifies the sound pressure, right? Many times, okay? Which is very important. Because to move the fluid, you need more pressure. To move the air, you need less pressure, right? So since we are moving the waves to the fluid, from the air to the fluid, we need to amplify the pressure. Make sense? To increase the pressure. Otherwise, fluid will not move. Okay. So the last ossicle is the steps, right? Which is attached to which window? Oval window, right? And in the other side of the oval window, you have the cochlea, right? So oval window is attached to the fluid, right? The other side, you have the fluid. So when the oval window will shake like this, the fluid will also move, right? That will create waves in the fluid. Okay, now let's see the cochlea, right? Cochlea is filled with fluid. It's a coiled structure, bony structure, right? Snail-like. You can make it straight and see inside it. How many membranes inside? How many membranes inside the cochlea? 2. Upper one is called the vestibular membrane. Lower one is called the basilar membrane. Is it clear? So how many chambers? 3. Uppermost one is the scala, vestibule, right? Or vestibuli. Middle one is the scala, media, middle one. And lower one is the scala, tympani. Is it clear? Okay. Now middle one is very important because the organ of Corti is located in the middle one, right? Sitting on what? Which membrane? Basilar membrane, right? And inside the organ of Corti, you have, why it is important? You have the hair cells. Those are the sound receptor cells. Make sense? So hair cells are located inside the spiral organ of Cortex, right? And spiral organ of Cortex is resting on the basilar membrane. Is it clear? Now you tell me, on the organ of Cortex you have a soft jelly-like membrane, right? That is called tectorial membrane, right? And here of hair cells are what? Inserted into it, like this. Make sense? Now let's go back to the oval window. Oval window is shaking like this, right? That is creating waves in the fluid, and under the basilar membrane you also have fluid. So that will move the basilar membrane like this. Make sense? So the hair will press against that tectorial membrane, right? When the basilar membrane moves up, that will bend the hair, right? Ions will get in, that will activate the cell, signal will go to. Straight, no signal. Bent, signal. Okay? So how many times the hair bends, that many times signal will go to the brain, sent to the brain, right? Brain will do what? Count that number, right? And will give you the perception, frequency of sound. Okay, yes?
Is there a reason why the cochlea is like so coiled? Is that what like stops?
Just to increase the surface area. So in a small inner ear, you have a coiled structure that has, if you see the basilar membrane, this is the basilar membrane, and this organ of Cortex is located on the basilar membrane like this, right? I have taken a section of it. So in this side, if you see, you have high frequency hair cells. Then gradually the frequency of the hair cells decreases. In this part you have medium frequency hair cells in this side, and you have less frequency hair cells, okay? So our range, human range is 20 Hertz. That means this, from this side, 20 Hertz to 20,000 Hertz. So these hair cells will be activated by only 20 times, 20 Hertz sound in 1 second. Makes sense? Very low frequency. As you go this way, the cells will be activated by higher frequencies. Okay, so very systematically organized. And these hair cells will be activated by 20,000 Hertz. That means 20 kilohertz sound. So all these hair cells should be present on the basilar membrane. Okay. So if basilar membrane is short, the hair cells will not be enough in number to keep it there. So that's why it is coiled, just to increase the area. Make sense? Increase the area. So all the hair cells of all frequencies are present there. Did you get it? There's like if I listen very low frequency sound, like 20 times per second, that is 20 Hertz, right? That will activate the hair cells here. So different part of the basilar membrane will be activated by different frequencies of sound. Okay. At this end you have the high frequency, this end you have the low frequency. Okay. So that I did not explain. We don't want to go into that detail. Okay. So on the basilar membrane, you have that organ of Cortex. Inside the organ of Cortex, you have the hair cells. Okay, and then the tectorial membrane, soft gel-like, resting on the organ of Cortex, and the pressure from the bottom will activate the cells. Here you see now, I have already explained, 2 membranes, 3 cavities. All 3 cavities are filled with fluid. And this is the basilar membrane, organ of Cortex, tectorial membrane. These are the hair cells. Okay? These are the hair cells here inserted into the tectorial membrane. Okay? And the basilar membrane will move up and down. the hair will bend and get straight. Two types of hair cells are present in the cochlea: outer hair cells and inner hair cells. Just know that auditory pathway, you see the cochlea is this one, hair cells, and these are the nerve fibers. That's the auditory nerve, also called vestibulocochlear nerve. Same thing. Auditory nerve is also called vestibulocochlear nerve, and which is cranial nerve number what? 8. Okay. That takes the signal to the primary auditory cortex of the brain, and on the way, signal is relayed in different structures. Cochlear nuclei receive the signal from the cochlea, then superior olivary nucleus, then the inferior colliculus, thalamus, and primary auditory cortex. You don't need to know all those structures. That's the pathway. Now, hearing loss. Two types of hearing loss occurs. One is called conductive hearing loss, and another type is called the sensory neural hearing loss. Now, what is conductive hearing loss? If I put a piece of cotton in the ear, you will not listen, right? If I block by something, you will not listen. So that is conductive hearing loss. Sound waves are not being taken inside the ear. So conductive hearing loss we can create right now, right? Make sense? If I give you pieces of cotton, you put in your ear, or ear plug, right? You use ear plug, that will block the sound from entering into the ear.
Does that happen with some people that have like too much earwax?
Yes, that is, that is also blocking the sound waves from entering. Anything that blocks, okay, the sound waves entering into the ear. So that is conductive hearing loss. Sometimes fluid accumulates, right? Or infection occurs that causes the blockage of secretion of fluid and blockage of the ear. So that is conductive hearing loss. If a tumor grows, that will also block the sound waves from entering into the ear. So all those belong to what? Conductive hearing loss, right? Is it easy or very difficult to fix? Depends, but rather easy, right? If wax is formed, you can clean it, right? Fluid accumulates, you can clean it. Infection, you can treat it, right? So that is easy to fix, relatively easy. Now, sensory neural hearing loss is the loss of the function of hair cells in the cochlea. Hair cells. If the hair cells are non-functional or destroyed, that causes sensory neural hearing loss. Now the problem is, in the organ of Corti, or in the inner ear, you don't have the stem cells. You remember when we talked about the olfactory system and gustatory system, you have seen the basal cells, those blue cells I showed you, stem cells. So if infection occurs in the nose, right, cells are destroyed, new cells will be quickly produced from the stem cells. In the tongue, you know, it happens all the time. When you drink very hot coffee or tea, after that, immediately after that, you will see the taste is gone, right? You don't taste the food because that heat destroys some taste receptor cells. Make sense? If it is too hot, right? And after an hour or so, taste comes back, right? Because we know that stem cells are there, they are producing new cells, right? But inside the ear, if the hair cells are destroyed, no stem cells are there. That's a big problem, right? So once the hair cells are destroyed, no new hair cells usually are produced. So that will cause the, hearing loss. Make sense? And once that happens, sensory neural hearing loss, it's very difficult to get recovered. Doesn't, we use the artificial cochlea also. So very recently they have found a few stem cells there, but they are not enough to replace. So that is conductive and conductive and sensory neural hearing loss. Now, what can cause sensory neural hearing loss? How do you think?
Too much noise.
Very good. Yeah. If someone works in a factory that produces very high frequency sound and he works for like long hours, right, without using the masks, that can cause the loss of or dysfunction of the hair cells. Make sense? Some toxic chemicals or drugs or chemicals can destroy the hair cells. Okay? Some drugs to treat the cancer that can also destroy the hair cells. Penicillin, high dose of penicillin can kill the hair cells. So some drugs or chemicals can also destroy the hair cells and cause the sensory neural hearing loss. Tinnitus. Tinnitus is ringing in the ear. Probably all of you already know that. Ringing in the ear. In the ear. Do any of you have tinnitus? It's not very uncommon. You will hear someone complains that no sound, no source of sound, but the person listens, noise or sound is produced in the ear. Sometimes it happens during sleeping. That's the problem, right? And if the frequency is low, that's okay. But if the frequency is high, happens very often, that causes a big problem, right? Person. And we don't know the exact reason for that. But now you already know that when the hair bends, signal goes to the brain, right? Now, if something bends the hair without the sound waves entering into the ear, intrinsically, if these hair cells are activated, intrinsically, without, any external waves getting in, brain only knows what? Brain is sitting in the dark, right? Inside the cranial cavity, extremely dark. Extremely dark inside the cranial cavity, right? So, brain doesn't see anything, brain doesn't hear anything. Brain only does what? Counts the number. Digital counting the number, okay? So how many times it gets the signal from the ear? Brain doesn't care if it is coming from outside or inside. Brain only cares how many times it is receiving signal from the receptor cells. Make sense? And based on that, brain gives you the perception. So if something intrinsically, activate the hair cells send the signal, you will listen the sound. Make sense? From the tongue, how many times the taste receptor cells are sending signal to the brain will count that. For example, if it is 5,000, it is sweet. If it is 10,000, it is sour. If it is 15,000, it is bitter. Make sense? So brain only counts how many times. So we know that sweet will activate the cells this many times per second. Another taste will activate this many times. So this is very interesting, right? That brain doesn't care. Is it sweet thing on your tongue or bitter thing on your tongue? Brain only cares how many times it is receiving the signal. Okay? Now if I put an electrode on the tongue and activate those cells will send signal to the brain, and brain will give you the perception. So we can create, artificial perception by activating the hair cells. So that's why phantogausia, those kind of things happen. Okay? It's intrinsic activation of the receptor cells. Okay, let's stop here.